In chapter 3, we're going to learn about logic. You may not realize this, but logic is very important in everyday life. All legal documents are written in logical language. When you registered for our My Lab course, you had to click on a terms of agreement. That's written in logical language. If you've ever served on a jury and you had to look at charges, formal charges, that's written in logical language. Whenever you look at a contract, it's written in logical language. So logic is very important. It's important for us to understand. The goal of this chapter is to determine whether an argument is valid or invalid. But to get that, it's going to take some work. So the first thing we're going to do, and this is in section 3.1, is we're going to look at statements, negation, and quantified statements. We're only going to be dealing with what we call a statement. So statements are either true or false, but not both true and false. So once we have statements, we can determine whether they're true or false, and that's going to help us to determine whether our arguments are valid or invalid. So let's look at some examples of statements. Honolulu is the capital of Hawaii. That's a statement. It happens to be true, but whether a statement is true or false, at this time, it kind of doesn't matter. We're just trying to determine if a sentence is a statement. This other example, taro is a fruit. Notice that that is a statement. It happens to be false, but it's still a statement. So what is not a statement? Not a statement would be commands, questions, and opinions. Go to the store. That's a command. Notice that we can't really say whether that's true or false. What time is it? That's a question. Is it true? Is it false? I have no idea. So since we can't determine whether it's true or false, it's not a statement. Titanic is the greatest movie of all time. So this is an example of a sentence that is not a statement because it's both true and false. For some people, Titanic may be the greatest movie of all time, so it may be true for some, and for others, no, it's not the greatest movie of all time. So this is an example of an opinion. So when you have an opinion and you apply it to the general population, that's not a statement. Now, if I were to change this and say, Jody Storm believes that Titanic is the greatest movie of all time, then I can assign a true or a false because that's just specific to myself. But notice this opinion is applied to the general population. So for some it's true, for some it's false. So not a statement. Again, we're only concerned with statements, things that we can tell are true or false. In all mathematics, what we use is we use symbols instead of words because they're easier to manipulate. So symbolic logic is where we represent our statements with lowercase letters. And typically we'll start with the letter P. So our statement, Honolulu is the capital of Hawaii, I can let P be the statement, Honolulu is the capital of Hawaii. And then I don't have to write that statement over and over and over again. I could just use the letter P. And maybe I'll let Q be the statement, taro is a fruit. So why do we typically start with the letter P? So in logic, we usually start with P, Q, and if we had more statements, we would do R, S, T, and so on. But it really doesn't matter. You can use any letter you wish to stand for your statement. So the question is, why do we even need to use symbols? Why can't we just keep everything in words? And I'm sure you can hear the roosters outside. Well, remember, this is a math course. We're going to be taking our statements and we're going to be manipulating them. We're going to be using the rules of logic. So we don't want to keep writing our statements over and over again. Here's an example of where we would prefer to use symbols rather than words. If you look at this statement, 5 times a number added to 4 is equal to 19. Actually, this is not a statement. This is a sentence because I don't know whether it's true or false. If I were to solve this, it's hard to do that the way it's written. So what I'm going to do is I'm going to replace all the words and phrases with symbols. So I can replace 5 with the number 5 times, and I'm going to use the multiplication dot for times, a number. Now I don't know what that is, so I'm going to assign a variable, and I could use x, I could use n. I think I'm going to use n for this number. So this is an example where we're using a symbol to represent, in this case, a word. Added to would be a plus. 4 is equal to would be the equal sign, and then 19. So once I've translated from words to symbols, then I can go ahead and solve this. So I have 5n plus 4 is equal to 19. Using properties of algebra, I could subtract 4 from both sides to get 5n is equal to 15, and then divide both sides by 5 so that we have n is equal to 3. So notice that it is difficult to solve this problem if it's still written in words, but once I change to symbols, then I can do my algebraic manipulation. And that's going to be the same idea when we're in words with our statements. We're going to want to play around with them. So we want to make sure we're comfortable going back and forth between symbols and words. Now that we understand what statements are, the first thing we're going to do is we're going to negate our statements. So we're going to look at what we call negations, and we're going to use this tilde symbol, that little squiggly line on your keyboard, for a negation. Now, if you've had logic before, you may have used a different symbol for a negation. Some other common symbols would be a subtraction sign or this weird L-shaped sign. But in this particular textbook, we use the tilde for a negation. So a negation does not make a statement false. What a negation does is it gives it opposite in meaning. So in other words, if a statement is true and you negate it, it goes to false. If a statement is false and you negate it, then it goes to true. In example 1, we want to form the negation of each statement. So part A, Honolulu is the capital of Hawaii. I want to negate it, so I simply replace is with is not to get Honolulu is not the capital of Hawaii. So notice Honolulu is the capital of Hawaii. That statement was true. When I negated it, it became false. Part B, 3 is not an odd number. Okay, that's a statement. I want to negate it. So there's an is not. I'm going to change it to is and write 3 is an odd number. So notice that 3 is not an odd number. That statement happened to be false. When I negated it, it became true. So the negation does not make the statement false. A negation just changes it from true to false or false to true. So sometimes we need to go from words to symbols, and sometimes we need to go from symbols to words. So let's go ahead and look at a symbolic representation, and this is fairly simple. And in fact, changing from words to symbols is really nice. Once you're in symbolic form, everything is nice. But remember, with words, there's many ways to say the same thing, so words can be a little bit confusing. Example 2, we have P, Honolulu is the capital of Hawaii. Q, 3 is not an odd number. So we're going to express the following statement symbolically. A, Honolulu is not the capital of Hawaii. So since P is Honolulu is the capital of Hawaii, Honolulu is not the capital of Hawaii, symbolically is not P. So you put the not in front of the statement. Part B says 3 is an odd number. My statement Q is 3 is not an odd number. So this is opposite of Q, or the negation of Q. So again, the negation goes before the statement. I'm negating Q. So we went from words to symbols. Let's go from symbols to words. Example 3, the statement Q, Honolulu has the world's busiest airport. So I want to express not Q in words. Now remember, there may be more than one way to write this. So if this says Honolulu has the world's busiest airport, I could say Honolulu does not have the world's busiest airport. Actually, I think in the US, it might be O'Hare in Chicago, might be our busiest airport. I don't know if it's the busiest in the world, though. Oh, okay. Now, that's not the only way I could have said it. I could have said, it is not true that Honolulu has the world's busiest airport. It is not the case that Honolulu has the world's busiest airport. Typically, we don't want to use those phrases before our statement because it's just more writing. We always want to pick the easiest way to write things. So the next thing we're going to look at is, we're going to look at what we call quantified statements. So quantified, quantity, it's describing a quantity. And quantified statements can be a little bit tricky. So the quantifiers that we're concerned with is the words all, some, no, or you might see none. And those are quantities that can be contained in a statement. So a quantified statement is simply a statement containing one or more quantifiers. Some examples of quantified statements would be all mathematicians are logical, some people are singers, no dolphins have feathers, some students do not study. So these are examples of quantified statements. So quantified statements can be a little bit tricky. So we're going to look at two things. We're going to look at equivalent ways that we can say a quantified statement, and then we're going to look at negations of a quantified statement. So when we look at equivalent ways of expressing quantified statements, now if this shows up in your homework, you could simply use this table because it's like a template. If we have a form all A are B, the example here is all mathematicians are logical. So that would be A would be mathematicians, B would be logical. So if you have a quantified statement of this form, all mathematicians are logical, an equivalent way of saying that is, well, since all mathematicians are logical, that means you can't even find one mathematician that is not logical, which gives the equivalence, there are no A that are not B, because all are. So none are not. So there are no mathematicians that are not logical. These two statements are equivalent in meaning. Again, this is not anything you have to memorize. You can always just look up this template that I'm highlighting. So let's say you have the form some A are B. Some is like saying at least one. So if we have some people are singers, equivalently, that means there's at least one person that is a singer, which is where the equivalence comes from. There exists at least one A that is a B. So there is at least one person that is a singer. These are equal in meaning. So I'm just going to put an equal here. The next form we're going to look at is no A, R, B. The example here would be no dolphins have feathers. No dolphins have feathers. So if no dolphins have feathers, then it must be true that all dolphins do not have feathers. So the equivalence is all A are not B. So again, these are equivalent. Last would be some A are not B. The example here is some students do not study. So that means there's at least one student that does not study. So at least one student that does not study equivalently could be not all A or B or not all students study. Now it may be a little bit confusing to see that these guys are all equivalent, but again, you don't have to memorize it. Just look at the highlighted table and you can use this to go back and forth in your equivalence. The fun part is when we negate quantified statements. So the negation of a quantified statement. So remember the negation says if it's true, it goes to false. If it's false, it goes to true. So now let's go back to our quantified statement. All A are B. The example is all mathematicians are logical. Let's say I want to negate that statement. So let's just say, oh, all mathematicians are logical. I'm going to make that false. Intuitively, people think that all will go to no, but it doesn't. All mathematicians are logical. To negate that, all I have to do is find just one mathematician that is not logical. And at least one is some. So some A are not B is actually the negation of all A are B. Some mathematicians are not logical is the negation of all mathematicians are logical. So these guys negate each other. Oops, I don't want that big line, I want this line. So they're negations of each other. If you have some A are not B, its negation would be all A are B. And intuitively, people don't see that. So if you're not sure why these guys are negations of each other, just look at the template and use the template. Some A are B. Some people are singers. That means there's at least one person that is a singer. And I'm going to say, no, that's not true. You can't even find one because no A or B, no people are singers. So notice that these do negate each other. So you could say this as all people are not singers. That's acceptable as well. Typically, when you're asked to negate a quantified statement in your MyLab homework, you'll have to begin with some, all, or no. So now let's just consider this statement, all numbers are even. And I'm going to show you why a negation of all doesn't go to no, a negation of no doesn't go to all. Okay? All numbers are even. Notice that this statement is false. 3 is a number, 3 is not even, so this statement is false. So if I negate this all statement, then its negation is going to be true. So let's just say that I said, well, no numbers are even. Let's say that I thought, okay, all negation has to be no because all and no are opposite. But the statement no numbers are even, that's also false. which can't happen. If I negate all numbers are even, then its negation has to be true, which is why the negation of all is not no, and the negation of no is not all. Okay? All we have to do when we have an all is find at least one that is not, or some that is not. Let's look at example 4, and then we'll kind of let that go on the back burner for now. You can follow the template if you don't get why these are negations of each other. Example 4 says the mayor told us all homeless will be given housing. I later learned that the mayor never tells the truth. What can I conclude? Well, what you can conclude is this statement is a lie, right? So this statement is false. So I can conclude that its negation will be true. So I can conclude that this all will be is the same as are. This all statement's negation will go to some will not, right? All will be goes to some will not. So some homeless will not be given housing. So some homeless will not be given housing is really what the mayor is saying because he lies. But this says express the conclusion in two equivalent ways. Well, remember we can always replace some with at least one. And I'm not going to say there exists at least one. It's sufficient to say at least one homeless. And it'll sound better if I say person will not be given housing. Okay, or you could say not all homeless will be given housing. And that's it for this section 3.1. We really just wanted to discuss what a statement is because that's all we're concerned with in this chapter is statements. We wanted to look at how we negate statements, and then we wanted to look at the special case where you have quantified statements. How can you say them in equivalent ways? How can you negate them? And that's it.